Hello students, my name is Shayan Mitra. I am the faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today I am going to take the class of LTI system response. In the previous three lectures I have described what is the convolution is, how the system works, okay, what is the linear time invariant system and what is the causal system, how could we decompose a signal into using the impulse signals. We can decompose a specific signal, we can feed all those signals to a specific system, and depending upon the system, if the system is linear time invariant causal system, we can work upon that. We can use that specific impulse signals as we can use that as an input. We can get the impulse response, and using that impulse response we can provide the proper output signal. So and that is also known as the convolution, and we have given different kind of examples, different kind of mathematical examples. In this specific lecture we are going to describe in case how the convolution is very much similar to the convolution of we have described of discrete time convolutions sum. Now in this, from this specific lecture we are going to describe how the continuous time convolution sum works, and that next lecture we are going to describe what is difference equation and what is the basic system properties of LTI system, where the stability and causality take a great importance, and we'll elaborate on that on the next two lectures. And this lecture we are going to describe, we will come up with different kind of examples to support our argument. Okay, so let's begin with the lecture, and this is the lecture number 10. Okay, yes, and the code name is the code name is this is the lecture number 9. Okay, yes. Okay, so begin with it. Okay, so you can see from this lecture that this is the representation of continuous time signal in terms of impulses, and that is the specific signal that we are talking about. Here what we have taken this is a continuous time signal, and the staircase is provided us with the proper logistics where we can find the value of the impulse response, and this impulse response can be rewritten as minus del from, we have taken stairwise property where we can find the impulses of the specific continuous time signal, and it could be written as here minus 2 del to in between minus 2 del to minus del. This is the, it could be assumed as a get function, it could be written as in this format. Okay, this is the function again. We can, so these are the, it means what it really appeared to be saying that in case of discrete time signal we have taken a xn signal, input signal, there is a discrete time signal. This is a continuous time signal, we have taken the different form. Now look, from minus 2 del to minus del, this is the first function of, okay, this one is the second, this is the third, and this is the fourth. And this way, after adding up all these specific signals, we will get this specific input signal. Okay, the same process that we have taken in case of discrete time signal, where the x function of n is the input signal. We decompose that signal in with using the impulse signals. Okay, and we fed them to the digital system. We will do the same thing in case of continuous time signal. In case of and this picture is showing that same thing, that this is the input, this is the continuous time signal. We decompose this signal in 5-4 different format. Okay, 5-4 different format. Okay, so if we just continue with this specific graphical representation, we would come to the conclusion here for the mathematical representation here, that is employed in discrete time case. The approximation can be expressed as a linear combination of delayed pulses. That's what I have described you. And this del of del t is can be written as that 1 by del is will be a finite value when it is in between 0 to del, or it will be 0 otherwise. And this could be written as, since del of del t has a unit amplitude, and this specific continuous time signal of the input signal can be written as the summation of k is equal to minus infinity to plus infinity, where the x of k del into del t minus k del into del. So the same process When in case of discrete time signal, we have used the same, we employed the same process where we understand a specific signal by decomposing it, and the same thing is we have taken the same route to understand the continuous time signal, where we are representing continuous time signal using the unit impulses. Okay. So after using the unit impulses, we can use this specific formation. Okay. This is the specific formation we are talking about. Okay, I'm sorry. This is the input signal. This could be written as in this format. Okay. Okay. So, and now when you are talking about this del value, now del value, what is the del value really applied here? This del value is basically approximation summation of the range of that impulse signal in between the specific signal is exist, and it should be, or it have to be tends to 0. Without that we cannot understand or realize the mathematical representation. Okay. So it could be written as the x function of t is written as limit del tends to 0. The summation is between minus infinity to plus infinity, and x k del is del t minus k del. Okay, this could be written here. Okay. Now if we approach to the next level, what we have here, that a also as del tends to 0, the summation of equation 2.26 approaches an integrate. Okay. This can be seen by considering the graphical interpretation of the equation illustrated in figure 2.13. This is the figure. Okay. The 2.3 figure is here. Okay. We are going to describe both, how the mathematical interpretation has been concluded and the graphical representation also. So using that we will be understand the same process has been applied in case of continuous time signal, also in case of discrete time signal. So now if we proceed here, what we have here is, now suppose yes, as del tends to 0, the summation equation 2.26 approaches an integral. This can be seen by considering the graphical interpretation of the equation. Okay, here we have illustrated the signal as x tau, del t minus tau, and their product. We have also indicated a shaded region whose area approaches the area under x tau del t minus tau as del tends to 0. Note that the shaded region has an area equal to x m del, where t minus del is m del is greater than equal to t minus del but less than equal to t. It means basically it provided us the space of del. The whole statement is trying to provide us the information that del, that what I have already discussed, that the del value, the del is basically tends to 0 value, it a very infinitesimal small amount in within which the amplitude of the impulse signal is present. Okay. For the value of t, only the term with k is equal to m is a non-zero in the summation of equation 2.6, and thus the right hand side of this equation also equals x of m del. Consequently, it follows from equation 2.26 and from the preceding argument that x of t equals the limit as del tends to 0 of the area under x tau into del of t minus tau. Moreover, from equation 1.74, we know that limit s tends to 0, and it could be written as this. And this is the you could say this is the convolution sum of a continuous time signal. Basic fundamental equation or fundamental mathematical representation of continuous time signal. It means that x function of t is written as x tau into del t minus tau d tau, which is the integration of minus infinity to plus infinity. So, and the same way this could be written as it could be said this is the shifting property, where the t is equal to the only value we will get when the t is equal to tau. Okay. So depending upon that, you can also set it as a shifting property. Okay, this is a shifting property. It could be said that. Okay. So next process is that suppose this is the ut, which is in between u tau del t minus tau, and it could be written as this format. Because we already know the step function will provide you the answer where provide you the value where the signal is suppose ut, it means that value of t should be greater than 0, greater than equal to 0. Other than that, the step function will provide you no value or 0 value. Okay. So now, so from equation 2.27, what we have understand, this equation should be viewed as an idealization of the sense that for del is small enough, the approximation of xt in equation 2.25 is essentially exact for a practical purpose. Equation 2.27 then simply represent an idealized equation of 2.25 by taking del to be vanishingly small. Note also that we could have derived equation 2.27, this equation, directly by using several of the basic properties of unit impulse that we derived in section 1. This is not important, we have already discussed what we are trying to imply here, that if the value of del is tends to 0, it will provide you the same mathematical explanation, and it could be understand using this mathematical representation. Now what the mathematical representation is saying here, that the integration minus infinity to plus infinity is between the integration of x tau into del t minus tau d tau. Now x tau can be written as x function of t del t minus tau d tau. Now this function is a constant for d tau, and it is not required. It is not required to integrate this specific x function of t, the continuous other input signal. Okay, so if we just put it out from the put out from that specific integration format, we will have del t minus tau d tau, which is in between minus infinity to plus infinity, and will only provide you the value of series of 1. And now if you multiply the value, this is the same process practically. If you take a close look in the previous lecture that we have described about the discrete time signal, we take the same steps here. Now as it is because a continuous time signal, we are using a different mathematical notation. Other than that, there is nothing is different. Okay, we only get the value of del t minus tau is equal to 1 when t is equal to tau. Okay, so depending upon the value of t, x of t, suppose is in between 0 to 4 or 0 to 10 or minus 10 to 10, so according to that we will get a summative value of the input signal, and it will only provide you the same specific input signal. So what it everything that again the we conclude to a same specific conclusion. We can conclude that as specific input signal can be rewritten as the summation of impulse signal. Okay, so that is has been written. Now if we take a closer look at the graphical representation here, it's also proving the same thing, that now suppose this is the input signal, continuous time signal. Now we have taken del t minus tau, the impulse signal, in this format. Okay, now when we multiply this signal with this signal, we have provided with this amount of value, and this shaded region that has been already mentioned before is that the value of del, which is tends to be 0, because as we take a small value of del, because we cannot have a discrete point where the value of the impulse signal is provided as the value 1. So we have taken a range of space or range of area in which or in between which the value of the signal anywhere in that region, the value of that specific signal is 1. Okay. So this is the conclusion that we are talking about. So now if we just proceed with this specific understanding. Okay, so these are the function. The same process has been taken care of here. Okay, del t minus tau, it could be written as here. So these are the process. Now in this case, what we have taken the del tends to 0. The del tends is so small that we are neglecting the width of this del. Okay, the same process will also be followed here when we are talking about the continuous time unit impulse response and the convolution integral representation of LTI system. It will take the same route to understand the continuous time signal. There is no basic difference, no fundamental difference when we are trying to understand a discrete time convolution integral or a continuous time impulse response and convolution integral experimentation. In case of discrete time, it has been known as convolution sum. In case of continuous time unit impulse, it has been known as convolution integral representation. Okay, so that is what now from that has been written here, we can understand that as in the direct discrete time case, it has been written here what I have already told, that the representation developed in the preceding section provides us with a way in which to view an arbitrary continuous time signal as the superposition of scaled and shifted pulses. In particular, the approximate representation in equation 2.5, the previous equation, the signal x tau t as sum of scaled and shifted version of the basic pulse signal. Okay. Consequently, the response of y tau t of a linear system to this signal will be superposition of the responses to the scaled and shifted version of del tau f. Specifically, let us define hk del t tau as the response of an LTI system to in the input del t minus k del. So basically, this output signal can be written in the same form, right? X k del, that where the del tends to 0, and h tau k del t tau. Now this h tau k del t tau is nothing but the impulse response of this specific impulse signal. The same process that we have taken in case of discrete time, we are taking the same process, the same method to understand output signal in case of LTI system, where the input signal can be rewritten as we have already know, the input signal can be rewritten now as the combination of impulse signals, and because we also are taking the linear time invariant system, we can use the additive and multiplication properties, and we are doing that. Okay, so this is the process, the same process. This is the input signal, this is the impulse response. Now when multiplied with this impulse response to the input signal, we are getting this kind of values, consecutive values. Now when we add up them, we get the output signal, and this is the input signal. Okay, we have taken impulse values. Okay, we multiplied them with the impulse response, and we get the output value, and this is the input value, and this is the output value. Okay, these are the process we are going to describe how this signal has been converted into this kind of a signal. Okay, so there will be error matching process are there. We limit these values, and we take the smooth edges, and we converted it to a phasing signal. So the same thing. Now this is the yt, it could be written here in this way, it could be written here also this way. This h tau can also be written as h tau t, and it could be written again in this format. Okay, the same shaded area. We have already discussed all the graphical representation. So this is the final formation, that same process that we can write this h tau t or h suffix 0 function of t in the form of h function of t. Now, so we can conclude that the output signal or the y function of t can be written in the form where we are taking the integration from minus infinity to plus infinity of x tau into h t minus tau. We are taking the integration within the limit of minus infinity to plus infinity of the function x tau into h t minus tau. Okay, using that same process. So in case of discrete time system, we have used the summation convolution sum, and in case of continuous time signal, we have used the convolution integral format. So this way we can conclude that the same process has been taken here. Just because of the signals properties are different, we have take different approaches, but the conclusion, the mathematical representation will provide you the same significance. Okay, so if we proceed with the same process, it could be written as the same way. Y of t is equal to xt multiplied by h function of t. Okay. Now we will consider some examples. Now if we take a close look at the example here, what has been said here, that let xt be the input to an LTI system. Okay, so one sec. So the first signal we are talking about is the first example, that here we have taken x function of t e to the power minus at ut a greater than 0, and the impulse response is a step function. Now what we have here is the same process, the same function that we have already analyzed this kind of function. Now we are going to do it again. Okay, this x function of t is written as e to the power minus at into ut. It could be written here this. So x tau into h t minus tau can be written in the form e to the power minus a tau, where the value of tau is in between 0 to t, and for other than the value in between 0 to t, if we put the tau value other than less than 0 or greater than t, the output signal will be a 0. So this signal and this signal, the graphical representation of h tau is this as a step function, and the input signal can be written here as it is a exponential signal but a decremental exponential signal. So it has been the nature is this, and same thing, we'll take the same steps. We first make it a reverse and we'll get this. Okay, so as we have added plus t, it will be advanced. It is not going to advance, right? This is the h tau, this is the h t minus tau. Okay, so this is the reverse value. Okay, yes, for t less than 0, right? That's what I'm saying, that when t has a negative value, it will be advanced, and when t has a positive value, it will be delayed, because we have taken a mirror image of h tau. Okay. So these are the ht minus tau for t greater than 0 and t less than 0, t greater than 0 and t less than 0. Okay, these are the input signal, this is the input signal, and this is the impulse response. Now if we multiply them, we will get this specific result. So how we will get that method? We will consider the mathematical representation and as well as the graphical representation. So if we start with the first, we will start with the mathematical representation. Now first we know that x tau into ht minus tau is equal to e to the minus alpha a t tau when the value of tau is in between 0 to t, and it is nothing but the output signal. So if we just put the output signal in the in accordance with, what we will get? We will get this as the yt. This is the output signal. For this expression we can compute for t greater than 0. We will have two different response, right? First one is t greater than 0. For t greater than 0, this is the t greater than 0 value. Okay, we will get the value, as we know that value of tau is in between 0 to t. So we will take the limit from 0 to t for integration, and the e to the power minus a tau d tau, we will integrate this specific function within the limit of 0 to t. Okay, and by doing that we will get this specific value minus 1 by a into e to the power minus a tau. Okay, and we will get this specific function. Okay, so for this all t, we will get the value y function of t is equal to 1 by a into 1 minus e to the power minus at into ut. Okay, so if we just put this in perspective, we will get this specific output function or output signal. You can say it in both ways, that output function basically provide you with the graphical representation, which is signal. Okay, so this is the first example that we have taken here. Okay, from this expression we can compute that y function of t is greater than 0, and the same process has been taken here. Okay, we have already knew now the important factor is why we have taken the value for t greater than 0. Now if we take a close look here, that this is the h tau and why is the signal? The signal is here. This signal is only if you just say it one way, it is a right hand side signal, right sided region. It only expand in the right sided region. So when you are talking about t less than 0, the impulse responses are all positioned on the left hand side region. Okay, so we will only consider the value which are present in the right hand side. Those values which are present in the left hand side will directly be discarded. Okay, so we will only take the values which are in between 0 to t and also where the value of t is greater than 0. Okay, the value of t need to be greater than 0. So that's why we have, when we are integrating the function, we have only taken the condition where the t is greater than 0. So in that region we will have the specific non-zero elements or non-zero values of that function. Okay, so this is the function. That's why we have taken the 0 to t function and we have integrated that, and we get the value 1 by a into 1 minus e to the power minus at. Okay, so this is the function that we are talking about, and it could be graphically represented in this format. Okay. Okay, so we will conclude our lecture here, and in the next lecture we will again talk about the continuous time signal. Now the one thing we need to understand, that we are the whole module, the second module that we are discussing right now, it will take other 2 lectures to complete, and this next 2 lectures I am going to with these few examples we are going to understand the stability and the causality of LTI system, and also the difference equation. Okay, and using that we will conclude this specific module. And the whole module that we are considering here, we have to understand this is a system that we are considering. We are going to discuss this specific topic in the next lecture also. Okay, thank you.